Let f be a function from a to b, then f is invertible if and only if f is injective and surjective. This is an if and only if statement. So we will prove two directions. The first direction is suppose that f is invertible. We need to show that f is injective and f is surjective. So this is the compound statement. We have two statements to prove this in logical end. So f is injective, the first part, and f is second. The second part is f is surjective. So we first prove that f is injective. Okay. So our hypothesis is f is invertible. F is invertible. F from A to B. So there must be an inverse function f inverse, right? Since f is invertible, and we know that exists a unique the function f inverse from B to A, such that so f send A to B, f inverse B to A, and f from A to B. So we have f compose f inverse. F compose f inverse is identities on B, and f inverse compose f is identities on A. Okay, f inverse compose f is identities on A. Using the two and a proposition or a lemma or theorem we proved before, we can, this is one way, we can quickly show that f is injective and surjective. So here's a theorem we proved before. The composition function g dot f is injective, then f is injective. G dot f is injective, so g dot f is injective. So we know that here f inverse dot f equal to identity on A. Recall that the identity function is both injective and surjective, right? This is bijective. So in particular, this function is injective. And f minus 1, f inverse, compose f is injective, then f must be injective. So f must be injective. So let's say by 2. Since f inverse compose f equal identities A is injective, we have f is injective. So maybe I should say a bit more. So look here, we have f inverse plays a role of G, and f is SF here. Oh, okay, f is injective. That's what this theorem 2 say. So f is injective. So that's the first part. We show that f is injective. What about the second part? F is surjective because and say second one. Next, show that f is surjective. So recall that we have this theorem, say theorem number 4. And now we have f dot f inverse is identity on B. F dot f inverse is identity. Identity is injective. We do it. Identity is surjective. So f dot f inverse is surjective. Therefore, by this theorem, f here now plays a role of G. So it must be surjective. So we call that since f dot f inverse identities on B is surjective by the theorem above, say theorem 4. We must have f is surjective. So now we both have f is injective and f is surjective. So we prove the first part or the first direction of the theorem. Okay, now we need to prove the other direction. Now assume that f is injective and surjective. And we know we have other term to say that f is bijective. We need to show that f is invertible. So recall that invertible is a function, so f from A to B is invertible if there exists a function g from B to A such that A, B, F, G, B to A, such that G dot F is identities on A. And F dot G is identities on B. This is what we need to show. Okay, so now we need to find such a function because we want to show that f is invertible. Therefore, we need to show that and it's invertible if there exists such z. We want to find such a z. We can find such z. Okay, so now we want to find the inverse function for f, right? Satisfy the two conditions. So we're going to construct z as follows. Now, to construct a function means that for any point small b in B, for any point small b in B, we want to define what is g of small b. What is this in A, right? So, for B in B, for this B in B, this one is mapped by something in A because this function is surjective. So it must be something here, small a, sent to B, right? So that's how we prove it. So now let B be an element in B. We will construct G of B. Okay, or we define G of B. Okay, as an element in A. So since function f from A to B is surjective, now B in B, there exists a unique, actually also injective. Surjective, there exists a B, but injective gives us this B, this small a is unique. Let me repeat it. Surjective means that for each B there exists a small a in A, such that B equal to f of small a. But injectivity say that this small a is unique. Okay, there exists a unique A such that B equal to f of A. So we can define, because we go from B in B, we get there exists a unique A in A. So this one can be defined as G of B. So we can define G of B to be so this exists a unique A. Okay, so now for each B, small b in big B, we can find a value in A. Okay, so the existence condition is good. Recall that for define a function we need two conditions, existence and uniqueness. So for existence condition, for each B in B, we can find one A in A. So existence condition is good. Now for this B in B, then B must map to exactly one point, just one point in A, and this is a uniqueness condition. So uniqueness condition is also good. So yes, so we define the function B, G, send B to this small a. Okay, so B, G is well defined. Now we check that G is the inverse of f, meaning that when you check, verify the two conditions. That is, we check the two conditions. Verify the two conditions. Okay, G dot f send A to B, B from G send to A. G dot f we can verify is equal to identities on A. Okay, so we have G dot f of x for x in A. G dot f of x is given as G of f of x by definition of composition. G of f of x is a number, or an element in B. Okay, this is an element in B. G of an element in B is defined as some small a such that f of a is equal to b. Okay, so this is defined as something. Let me call it z. Okay, for the moment, just say z in a, where z f of g is this exact this point, right? The point, the element in B, f of x. But since f is injective, right? Since f is injective, this gives us z equal to x. Injective, we know that g must be equal to x. So g dot f of x is exactly x. Okay, this means that this one, g dot f of x, is the same as identities on a of x for all x in a. Therefore, we know that g dot f must be identities on a. We can do it similar to prove that. So the first condition is good. We do similarly for f dot g equal to identities on B. So now g, we know that's a function we construct from B to A, and A map via f into B. So this is f dot g from B to B, and we can show that f dot g is identities on B. That's our second part. To verify the condition. Okay. So now we have for small b in big B, f dot g of small b is f of g of small b by definition of composition. G small b, so this is small, say this is small b in big B. G map this one to g of b, just a point on A, an element in A, right? So that g of b is defined as A, where A is such that b equal to f of A. So we call or note that g of b equal to small a, where we call that g of b so we call that g of b equal to a, where f of a equal to b, as a definition, as in the definition of function g. Okay, so this is f of small a, where small a is given by f of a equal to b. Okay, so we know that f of a equal to b just because right here f of a is equal to b. F of a is equal to b. So here we have f dot g of b equal to b, but b is the same as identities on b of small b. So these two functions must be equal. F dot g must be the same as identities on b. Therefore, f dot G must be identities on B. And this is the second condition we need to show. So we show both conditions. F dot G is identities on B. Therefore, G is the inverse function of F. Okay, and which means that there's G satisfies the two conditions. Therefore, F is invertible and G is the inverse function of F. So F is invertible and G defined above is the inverse of F. And so we prove that if F is injective and bijective, then F is invertible. So we finish the second direction. Therefore, we are done with the proof of the theorem.